Hello, Chemistry 30. This is our 8th lesson in the Thermochemistry unit. This is complex thermochemistry problems. In this lesson, we will work through 2 examples. Example number 1. Hydrogen sulfide gas burns in excess oxygen to produce sulfur dioxide gas and liquid water. Find the heat released when 100.0 grams of H2S is burned. Pause the video and attempt this example. This is a combustion reaction, which is a potential energy change. So we will use the equation delta H equals NH, and we will be looking for delta H, the heat released. The only problem is we don't know the H value for the combustion of H2S. But we can use Hess's law mathematical to find the delta H of the general combustion equation, then divide by the coefficient in front of H2S to get the molar enthalpy of combustion for H2S. We can then solve for delta H equals NH when 100 grams is burned. First, we need a balanced chemical equation. We are going to use Hess's law mathematical to find the delta H of this general combustion reaction. So we need the heat of formation of each substance in the chemical equation. The heat of formation for H2S is 20.6 kilojoules per mole. Don't forget it's a minus. The heat of formation of O2 is 0 because it's an element. The heat of formation of liquid water is negative 285.8 kilojoules per mole. And the heat of formation of SO2 gas is negative 296.8 kilojoules per mole. We can then solve for our target delta H value by taking the sum of the heat of formation of the products minus the sum of the heat of formation of the reactants. Don't forget we're timesing each heat of formation value by the coefficient in front of each chemical species. And our target delta H value is negative 1,124.0 kilojoules. We can express this in the chemical equation by putting it on the product side. That means this is an exothermic reaction. Now we can solve for delta H because we have the values of N and H. We are starting with 100 grams of H2S. We are then going to divide it by the molar mass of H2S, which is 34.09 grams per mole. And we're going to times that by our H value, the molar enthalpy of combustion of H2S, which is the negative 1,124.0 kilojoules, which was in the chemical equation, divided by the 2 moles, the coefficient in front of H2S. If we perform this calculation, we are left with a heat released value of negative 165 times 10 to the third kilojoules. Example number 2. A waste heat exchanger is used to absorb the energy from the complete combustion of hydrogen sulfide gas. What volume of water undergoing a temperature change of 64 degrees Celsius is required to absorb all of the energy from the burning of 15 kilograms of hydrogen sulfide? Pause the video and attempt this example. This is a heat lost, heat gained type of question. So we have the combustion of hydrogen sulfide, which will be losing energy and is a potential energy change. It will equal energy gained by the water, which will be a kinetic energy change. And we are looking for M, the mass of water. We can use the H value for the combustion of hydrogen sulfide, which we solved for in example number 1. Once we have the mass of water, we can then convert it to volume, assuming that the density of water is 1 gram per milliliter. We will be using the equation negative NH equals MC delta T. And to solve for M, rearranged, M is equal to negative NH divided by C delta T. We have to solve for N first, the moles of H2S. So we're starting with 15 kilograms. We are going to times that by 1,000 to convert that value into grams, and then divide it by 34.09 grams per mole, the molar mass of H2S. This gives us 440.011 moles of H2S. We also need our H value, which we can get from example number 1. This is the molar heat of combustion for H2S. So we're taking our negative 1,124.0 kilojoules and again dividing it by 2, the coefficient in front of H2S. This gives us a value of kilojoules per mole. But we do need to convert this to joules per mole for our final equation. So we will times it by 1,000, giving us a value of 562,000 joules per mole. We can now put this into our equation where M equals negative NH divided by C delta T. So we have our mole value times our joules per mole, and this will be divided by the specific heat capacity of water times the temperature change of water. This calculation should yield an answer in grams, which we can then times by 1 milliliter over 1 gram, the density of water, to give us a final answer of 9.2 times 10 to the 5th milliliters of H2O. Moving forward, we have the thermochemistry unit test.